This video presents the part of C work related to the use case number 3 of AtelierB project, the Railways application of AtelierB partner. The interaction between the static analyzer of C software, named Frama-C, and the development framework named the AtelierB, will be described. The software analyzer Frama-C has been developed by C AtelierB in the Software Reliability and Security Laboratory. It allows the validation of software written in C language, based on a specification language dedicated to C code named AtelierB. The C language is precisely the one in which is written the final code of the Railways application to validate. AtelierB gets this C code at the end of a development process that follows the B method supported by the AtelierB. The design of the application starts with the writing of high-level requirements in B language. These requirements are progressively refined into a low-level imperative specification in a language called B0, that is close to an executable programming language. So, these low-level requirements can be automatically translated into C code. The AtelierB performs some consistency checks of the high and low-level specifications. In addition to that, it performs formal proofs during the refinement process, ensuring that the B0 description is compliant with the high-level requirements. The objective of the interaction between Frama-C and the AtelierB is to reach the same level of confidence for the generated C code. Formal proofs can also be done by Frama-C ensuring that the final C code complies with the B0 requirements, assuming that these requirements are translated into AtelierB specifications. Today, AtelierB ensures the compliance of the generated C code with the B0 description in using two different translators from B0 to C. These two translators have been implemented by two independent teams. At the end, the generated C code from a B0 description is accepted only if the two translators give exactly the same result, spaces included. Verifying the C code against the B0 description with Frama-C would subsume this task in a more formal and flexible way. A formal proof in COC of the soundness of the approach has been established as first result. For the fun, that proof has also been done in AtelierB with Frama-C. The proved theorem is that a B0 description is refined by a C code when the code C satisfies the related AtelierB specification, and has no more requirement. This last point implies the verification that translation to C, done by the AtelierB, does not introduce runtime errors. Both checks can be made using Frama-C plugins. The presentation will continue on demo about the first verification, with the plugin performing the weakest precondition calculus named WP. It's time for a 6 minutes demo. The B project files have been given by AtelierB and content some representative examples of their applications. The demo will focus on one operation of the B machine named Donnies. This file contains the low-level requirements of that machine in the B0 language. Let's open the file with the AtelierB just after running a tool, showing a read circle on click events. There is the file with the B0 description. The considered operation is named get_C1du. That operation calls another operation, an internal one defined there, that will be not validated during the demo. We will just suppose that this operation is correctly implemented for. The demo will show how Frama-C can be used to verify that the related C code complies with this B0 operation. The B0 description has been translated into an AtelierB specification file. The C file generated by the AtelierB that implements the B0 description of all operations of the machine named Donnies is there. Just have a look at with a text editor. We can see the considered operation get_C1du, and below the second line of code calling to the other operation. Now, let's have a look at the AXL specifications, containing the translation of the B0 description of the operation. The function contract asserts the function assigns one output named *PO, and ensures that output is forced by that predicate. We have a similar contract for the called function. The output is the same, but the constraint differs. The difference between these two predicates will be about their definition. One of them will be fully defined, the one related the C code to validate. That second predicate is also used into the definition of the other. It remains as abstract as possible. We just have to know what are the data used as inputs, or as outputs by the called function. This translation into AXL comes directly from the B0 description of the operation. The verification of the considered function is modular and supposes that the called functions behave correctly. They set the good constraint between their outputs and their inputs. Let's now run Frama-C, using the demo script. It sets some parameters for the weakest precondition plugin that will perform the formal proofs and build, at the end, a report from a template file. It will load the generated C file, and import of the AXL specifications. First, we will select the WP plugin among the available plugins performing other static analyses, and open the panels specific to the proofs, done by the weakest precondition calculus. Selecting the function of validate, we can see the original source code issued from the AtelierB, and reveal the result of the import of the AXL specifications. Selecting the ensures property, the original AXL specification appears in second frame. Now, let's ask the weakest precondition plugin to perform the proof of the ensures property. The green bullet means that the formal proof succeeded. On a such example, it was automatic and required the external prover named alt ergo. We can do the same with the assigns clause. Here, the proof is splited into for proof obligations. Each of them succeeded and was proven by the internal simplifier named QED. At the exit, a report is built. We can have a look at it. It recalls the name of the checked functions, and for each of them gives the rate of success, here 100%. The ratio in terms of AXL properties. Then, there is some details for each properties. At the end, there is a global validation summary. We can conclude that, assuming the called function is correctly implemented, the C code has no runtime errors, then the statically analyzed C function can be formally considered as a refinement of the related B0 description. The validation of the absence of runtime errors can also be verified using Frama-C.